So we've looked at a whole heap of different variations of the basic curve or the function. We've squared it, we square rooted it yesterday, we found absolute value the other day, we've done all sorts of things. So I'm just going to finish off the topic, just have a look at other graphs. So by going through some past HSC ones so you can see the sorts of things that have been asked. So 2003 paper, there was their curve. They didn't actually give us the equation of this, but you might recognise it. Anyone recognise what this is? It's the reciprocal of a parabola. Because if you had, it would be an upside down parabola, it would go through -1 and +1, so that would be x. Well, it's upside down, so it'll be x plus 1, 1 minus x, but then it has must be times 2, because it has a y-intercept of 2. So, but anyway, you don't need to know that for this. It's just curious whether anyone recognise it. The first one they asked us to do was the reciprocal. Now, of course, if you did recognise that, then you'd know the reciprocal straight away was the upside down parabola. But if you don't, we'll just go through the process of turning our curve upside down. So the first thing, locate where 1 is. Well, they've given me a scale there by saying that's 2. So I know 1 obviously is halfway through. Our vertical asymptotes will turn into x-intercepts, sort of. So I've put point discontinuities on there. -1, when I turn that upside down, will still be -1, so that'll remain. 2, when we turn that upside down, that'll be a half. Now, yes, I did say it was meant to be a parabola. You may not recognise the shape I'm about to draw as a parabola. Trust me, that's a parabola. There is no bump there, okay? It does not exist. That is it. So you've got that upside down parabola, but because you're not actually drawing y equals 2 outside, or what did I say it was, 1 plus x, 1 minus x, something like that. You're actually drawing 1 over the function. We have the point discontinuities on the x-intercept there. So that was the first curve they asked us to draw. So the next one was quite interesting. Function x plus the absolute value of function x. Well, we've got function x. I guess the next thing to work out is what is the absolute value of function x, and then we'll add the two curves together. So absolute value of function x, that's the one where we get what's below, reflect it above. So the section in between -1 and 1, that'll stay the same, but those two, well, let's call them hyperbolas, will reflect up. I'm going to add these two things together. So in between -1 and 1, I'm going to have twice the value of that curve. So all those y values will double. So I know that 2 will go up to 4, and I'll get some sort of U shape. Now, the big mistake people made was to go, oh, well, hang on, the other sections, they're going to cancel out. And so they just did the U. Well, they don't cancel out. They get a value of 0. So therefore, we're on the x-axis with a point discontinuity, because we can't, all of a sudden, that vertical asymptote can't become a value, but it would just be the x-axis outside, because when we add those two curves together, we'd get 0. A lot of people forgot about that bit when they did that one. Square the function. Okay, so what do we know about squaring? Well, if I square 2, I'll get 4. When we square the bit below, obviously it's going to become positive, and it'll be a bit steeper because the y values are increasing. So we get that particular shape. Now here's the sort of one we haven't looked at yet, where we find some function of the function. So we get some function that we know, but instead of saying function x, so instead of doing e to the power of x, we're doing e to the power of this graph. The way I like to do these is, to the side, I like to draw the basic curve that I'm going to be using, and so to keep a track of what are the important features. So if I was to draw e to the x, I know that would be 1, and so I've got my exponential curve there. Now remember, we're not saying e to the power of x, we're saying e to the power of the y values of this curve. and we've got to come up with a graph. Well, what are the key things over there? We know that e to the power of 0 will be 1. Always will be 1. So whenever this curve is equal to 0, we know it'll be 1. Well, we don't have any value of 0, but we do have a horizontal asymptote at 0. So that means my new curve will have a horizontal asymptote at e to the power of 0, which is 1. Is that the first thing I did? Let's see. Oh no, first thing I did was to actually find the derivative so I can see what happens to any stationary points. So stationary points of the original curve, f dash x would be equal to 0, so the derivative of this will also be 0. So there'll still be stationary points at those x values. Well, there's only one stationary point, but at x equals 0, we know that. Okay. So e squared, 2.7 squared, whatever that is. So I've moved up the top there. Now, if you have a look at what an exponential curve does, so that stationary point was at 2, or the y value of 2, I should say. And after that, those y values are getting bigger and bigger and bigger. Well, what happens to our exponential once we get past an x value of 2? The curve is going up to infinity. So this curve must also raise to infinity for those particular function values. It would get bigger and bigger. So we've got that sort of U-type shape, but it's sort of more of an exponential than a parabola, but in two halves of it. Now, the other side. Okay. Point discontinuity, there. Well, because we know that doesn't exist. Horizontal asymptote, which I talked about before. Let me go back to those point discontinuity. Well, how did I know that? The original function is going off to minus infinity. Our curve, as it's going off to minus infinity, it's going towards 0. So this new curve we're going to draw must be approaching 0. That's why I've got the point discontinuity at 0. Okay. I've got there, it's got to bend towards the asymptote. E to the power of something is always positive. You've got two choices, really. Now, no cheating and looking at what the graph actually looks like on your sheets, but it could do one of two things. Let's have a look here. There's that. It could do that, bend towards the asymptote, or maybe it does that and inflects. How do we tell? Well, what's the difference between the two? And I guess the difference between the two is the gradient at that point of discontinuity. Right? One is approaching 0 because it's coming in and going sort of almost flat, almost. The other is approaching a larger number. So let's have a look. Our derivative is f dash x e to the function x. We're saying the function value is approaching, now we're going towards that, is approaching negative infinity. So if we have a look here, f dash x times e to the function x, well, the derivative of my original curve, that's approaching infinity, if you like, so it's quite large. E to function x is approaching 0. Infinity times 0, oh my god. I mean, what's that? But that's when we come down to the idea of dominance. And an exponential will always dominate because it'll go steeper quicker. It was the exponential that was approaching 0. So therefore, it's the one that inflects. It's the one that inflects. Okay. I can see some confusion. Right. So let me go over that again. What I'm saying is the derivative is f dash x e to the function x. So I want to see whether the derivative at our point discontinuity there, is it going towards 0 and going flat, or is it going steeper, going towards some positive number? That will tell me how the curve will come in. My derivative is made up of e to the function x. Well, e to the function x, we've already determined that goes towards 0. That's why we had the point discontinuity there. So we know that part's going towards 0. But what's the slope of the original graph doing at that point? Well, the original graph, the slope, is getting very, very steep and going towards infinity. So we had one function saying, hey, we're going to infinity. We have another function saying, hey, we're going to 0. How do I choose? And that's when the idea of dominance came up. Because an exponential will always dominate. Remember, in polynomials, it's the leading term dominates, things like that. How do you know which one dominates? Which one gets steeper quicker? And exponentials always get steep very quick. Keep an eye on those sorts of things. Have a think about that. What's the slope doing? Okay. I think most people would have gone the other one. They would just say, oh, it's bending towards the asymptote. That probably was the one most people went for. As I say, it's actually the one that inflects. Okay, let's have a look at the 2002 graph. So this one's a little bit more of a unknown graph. I mean, maybe it's a polynomial, but there's no way of telling. I mean, we've got some points they've told us, but we can't really determine for sure. I mean, see, this is sort of bending. If it was a polynomial, it would go straight up, I think, rather than starting to go concave. So who knows what that graph is. But again, we don't need to know the equation. We can use our ideas. Once again, the first one they asked for was the reciprocal. Okay, key points. Well, those x-intercepts will become vertical asymptotes. We know that. Okay. What else is key? 1, because when we turn 1 upside down, we get 1, and when we turn -1 upside down, we get -1. So -1, that one will stay there, and up there 3, 1. That's why I guess they've given us those points so we know where to locate 1 on our graph. Well, this curve keeps going on the left, so at somewhere it'll be -1 again, so I've just plotted roughly where it'll be. I've just worked out which region the curve's going to be. So remember, when we turn it upside down, what happens? Well, if it's below 1, turn upside down, it goes above 1. When it's above 1, turn upside down, it goes below 1, and so on. So basically it swaps the regions that it's in. And I'll just draw it. Remember, the stationary point is still a stationary point, but instead of being concave up, it's now concave down. Wherever the original curve's increasing, my new curve must be decreasing. Got to bend towards the asymptotes. This horizontal asymptote must be there because the original curve's going off to infinity. So if you think about, oh, we'll turn infinity upside down, we kind of think of that as 0. So we've got a new horizontal asymptote out there at 0. So there's our reciprocal. Y squared equals function x, which sounded like a good one to do, but when you look at this curve, it's not that great. I thought it was a bit boring, because of course anything where it's negative goes away. Remember, the first thing we have to draw is y equals the square root of function x. So anything below disappears. So we've now just got that little branch of the curve that we have to find the square root of. Now, I'm assuming that's a single root there, so it's cutting like a linear function, so I would anticipate then that the square root of that would be like a parabola on its side, something like that. However, there was a little twist in this one, and what a lot of people forgot was that single point there. Remember? Because the original curve existed at the origin. And you find the square root of 0, it's still 0. Yes, everything below disappeared, but that single turning point still exists. It can't go anywhere because it can't be the square root of a negative number. So you end up with a single point at 0 plus our, whoop, there it is, wow, a sideways parabola which didn't quite work out. Trust me, that is a vertical tangent. It might look like it's leaning in a bit. Use your imagination. Mind you, it'll be quite clear that it is leaning in a bit because I still have one more thing to do. I've drawn y equals the square root of function x. To get y squared equals function x, yeah, honestly, that is vertical. That is vertical there. All right. The absolute value of function absolute value x. Okay, so I think the way I'm going to approach this is if I do function absolute value x first, because it's just like parentheses, you start on the inside, work your way out, and then we'll find the absolute value of that new graph. So function absolute value x said, that's the one where we reflect in the y-axis, isn't it? So the left-hand side, see you later. Right-hand side reflects over. So there's function absolute value x. But we want the absolute value of that. So now anything that's below is reflected above. Oops. Okay. The log of function x. So again, I might just draw myself a log curve to the side so I can work out what the important things are. So my log curve does that. Goes through at 1. But that is, of course, y equals log x. We're saying the log of all these function values. Well, let's remember, what does our log curve do? We can't find the log of a negative number. Notice it's not saying the log of the absolute value of function x. It's saying log of function x. So again, everywhere where it's below the curve, and in this case 0 as well, because you can't find the log of 0, that'll disappear. So once again, we're only working with that section of the curve. Now I've drawn a vertical asymptote there because log 0 undefined. It might end up being a point discontinuity. I'm not sure, but I'll put the vertical asymptote in there to remind me. Yeah, that's where it's going to be. Okay, we've got a key point there, 3, 1. Well, the log of the y value. So log of 1, if we look at our log curve, log of 1 is 0. So there's going to be an x-intercept down there at 3. Now what happens either side of that? Well, either side of that we must have our log curve. Because on the left-hand side, these y values are going from 0 to 1. Well, look at our curve. As x goes between 0 and 1, so it is going to be a vertical asymptote, it looks like. And it'll come up, and then on the right-hand side, log of value is bigger one, it's going to be like a log curve as it comes through. So that would be log of function x. All right. So 8h is a handful there. Those function ones are always interesting ones to think about, because you've got to think about what does the actual curve do, find some key points to get an idea.